Our study of water would be quite deficient without a consideration of its ability to dissociate into an ionic form and thereby influence pH. This is yet another property of water that makes it the universal solvent. In this lesson, we'll be using what is known as the Bronsted definition of an acid and base. In this definition, an acid is a molecule capable of donating a proton, and a base is one that can accept a proton. We use a general formula of HA, as illustrated here, to represent a weak acid, which has a tendency to dissociate to a hydrogen ion or proton, and its conjugate base, represented here as A-. Notice that since this is a weak acid, the dissociation is represented as incomplete. The two-way arrows indicate a state of equilibrium between the two forms, acid and conjugate base. We can therefore derive an expression for the equilibrium constant, or Ka, which describes the ratio of dissociated to undissociated forms. Note that this is a dissociation constant, so that as the value increases, more of the acid has dissociated, indicating greater acid strength. We might more properly represent the reaction as given on the bottom of the slide, to show the participation of water. Dissociation of the acid results in water accepting the proton to form a hydronium ion. Water itself may be considered a weak acid. It can dissociate into a hydrogen ion and a hydroxide ion. Therefore, there is a dissociation constant, or Ka, related to the ionization of water. In fact, water is a very weak acid, so that in pure water the concentration of the unionized form is as high as 55.5 molar. If we include the concentration of unionized water with the Ka, we can define a new constant, the Kw. This is the ion product constant of water and represents the product of the concentrations of the ionized species. That is, the concentration of hydrogen ion times the concentration of hydroxide ion. This value is therefore a measure of the tendency of water to dissociate into ionized form. We can determine this value by measuring the concentration of H+ in pure water. Note that because water is essentially a monoprotic acid, the stoichiometry tells us that the concentration of the two ionized forms must be equal. That is, as one water molecule dissociates, it forms one proton and one hydroxide ion. We find that the concentration of hydrogen ions at 25 degrees Celsius is equal to 10 to the minus 7th molar, which must also be the concentration of hydroxide ions. Therefore, our ion product constant must be 10 to the minus 7th molar squared, or 10 to the minus 14. Since the quantity of dissociated water is so small, we can convert the number into a positive integer by taking the negative value of the base 10 log. An increase in pH by 1 unit therefore means a tenfold increase in hydrogen ion concentration. It also means that as the concentration of hydrogen ion increases, the pH decreases. We can define neutral solutions as having a pH of 7 where the ionized forms are exactly equal. Values lower than 7 would be more acidic, and higher values would be basic. Earlier we defined an acid dissociation constant, or Ka. Most biological acids are weak acids, like water, and therefore their Ka values are also very small. We can therefore convert them to whole integers by taking the negative log base 10 of the Ka. This gives us the pKa. Recall that as Ka increases, the acid dissociates more and is therefore a stronger acid. Since the pKa value is on a negative log scale, as Ka increases, pKa decreases. So then, in comparing acid strength, the lowest pKa would indicate the strongest acid. In our next lesson, we want to establish a relationship between pH and pKa.